Welcome to the Sleepless Universe. In this video, we'll explore some of the most fascinating theories about parallel universes, from cosmic inflation to quantum realities. If you enjoy this kind of content, please leave a like and subscribe. Now, I wish you deep relaxation and an enjoyable journey through the cosmos. Level 1 Multiverse, infinite space, infinite worlds. Imagine looking up at the night sky and knowing that somewhere, in the vast expanse beyond what your eyes can see, there exists another version of Earth, not just similar to ours, but identical in every way. Another you, gazing up at their own night sky, having the exact same thoughts at this very moment. This isn't science fiction, this is the profound implication of the Level 1 Multiverse, where infinite space gives rise to infinite worlds. The concept emerges from a surprisingly simple observation about our universe. When we peer deep into space with our most powerful telescopes, we discover that the universe appears remarkably uniform. Galaxies are distributed relatively evenly across the cosmic web, matter follows predictable patterns, and the fundamental laws of physics remain constant as far as we can observe. This uniformity suggests that space continues beyond our observable horizon, stretching endlessly in all directions. Our observable universe extends roughly 46 billion light-years in every direction, a sphere containing everything we can possibly see or detect. This boundary isn't a wall or edge, but simply the limit of how far light has traveled since the Big Bang began 13.8 billion years ago. Beyond this cosmic horizon lies more space, more galaxies, more stars and planets, continuing indefinitely according to our best understanding of cosmology. The mathematics behind this infinite expanse rest on solid foundations. Einstein's equations of general relativity, combined with observations of the cosmic microwave background radiation, suggest that space possesses a flat geometry. Unlike a curved surface that eventually loops back on itself, flat space extends infinitely in all directions. This geometric flatness has been measured with extraordinary precision by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft, confirming that our universe's curvature is indistinguishable from zero within observational limits. If space truly extends infinitely, and if matter continues to be distributed uniformly throughout this boundless expanse, then something remarkable must occur. With infinite space and a finite number of ways that matter and energy can arrange themselves, every possible configuration must eventually repeat. The laws of probability demand it with mathematical certainty. Consider the atoms that make up your body. Each atom can occupy different positions and states, but the number of possible arrangements, while astronomically large, remains finite. In a finite volume of space roughly the size of our observable universe, there are approximately 10 to the power of 120 possible ways to arrange all the particles. This number dwarfs human comprehension. It exceeds the number of atoms in our observable universe by an almost incomprehensible margin, yet it remains mathematically finite. Now, extend this reasoning across infinite space. If you have infinite attempts at arranging a finite number of possibilities, every arrangement must occur not just once, but infinitely many times. This mathematical inevitability means that somewhere in the infinite expanse beyond our cosmic horizon, there exists another region of space identical to our observable universe in every conceivable detail. Another Earth orbits another sun in another Milky Way galaxy, populated by another version of everyone you've ever known, living through identical experiences moment by moment. The calculations involved in determining these distances stretch the limits of mathematical notation. Scientists estimate that the nearest region containing a perfect copy of you would be located approximately 10 to the power of 10 to the power of 115 meters away. This distance is so vast that standard notation becomes meaningless. If you attempted to write this number using conventional digits, the resulting string of zeros would be longer than all the books ever written in human history, longer than the DNA sequences of every organism that has ever lived on Earth. But perfect duplicates represent only the most extreme case of cosmic repetition. Long before reaching such identical copies, you would encounter regions with increasingly similar arrangements, A near-identical Earth might exist merely 10 to the power of 10 to the power of 29 meters away. Still an unimaginably vast distance, but infinitesimally small compared to the perfect duplicate. This nearby twin might differ from our world by only a single atom's position, creating a planet virtually indistinguishable from ours in every meaningful way. Between here and these various duplicates lie countless near duplicates, worlds where history unfolded almost identically to ours, but with progressively larger variations. Perhaps in one region, you chose tea instead of coffee this morning, creating a butterfly effect that ripples through subsequent events. In another, the asteroid that ended the age of dinosaurs struck at a slightly different angle, altering the course of evolution in subtle but meaningful ways. In yet another, the continents formed different shapes during Earth's geological youth, creating entirely altered geography, while still supporting familiar forms of life. These variations extend far beyond Earth to encompass entire cosmic histories. Some regions of space experienced slightly different quantum fluctuations during the universe's inflationary epoch, leading to galaxies that formed at different times or in different configurations. The cosmic web of dark matter might have evolved differently, creating alternative patterns of galaxy clusters and cosmic voids. Stars in these regions might have formed with different compositions, giving birth to solar systems unlike anything in our local cosmic neighborhood. The infinite space allows for every possible cosmic evolution to play out somewhere. Regions exist where the first stars ignited earlier, seeding space with heavy elements sooner, and enabling planet formation to begin billions of years ahead of our cosmic timeline. Other regions experience delayed star formation, creating younger universes where complex chemistry is only now beginning to emerge. Every possible permutation of cosmic history, from the grandest galactic mergers to the most minute stellar variations, manifests across the infinite landscape. This concept fundamentally challenges our intuitive sense of uniqueness and specialness. Humans naturally feel that our experiences, our planet, our very existence holds something irreplaceable and singular. We perceive our personal histories, our relationships, our achievements as unique tapestries woven from countless individual choices and circumstances. The Level 1 multiverse suggests instead that this perceived uniqueness is an illusion born from our necessarily limited perspective. What seems singular and precious to us, your first memory, your deepest relationships, your greatest accomplishments, exists as one instance among infinite repetitions throughout space. Every moment of joy you've experienced, every challenge you've overcome, every person you've loved, all repeat endlessly across the cosmic expanse in countless identical scenarios. Your most private thoughts, your most personal experiences, your most individual characteristics are shared by infinite versions of yourself scattered throughout infinite space. Yet this infinite repetition doesn't diminish the meaning or significance of our existence. Each instance remains equally real, equally important to those living it. The fact that other versions of you exist across infinite space doesn't make your current experience any less meaningful, authentic, or valuable. Your thoughts, emotions, and relationships remain genuinely yours, carrying the same weight and significance regardless of their repetition elsewhere. The love you feel, the beauty you perceive, the satisfaction you derive from accomplishment, all retain their full meaning within your local experience. The Level 1 multiverse also provides a comprehensive framework for understanding cosmic evolution on the grandest possible scales. If space is truly infinite, then every possible way the universe could have developed from its initial conditions must exist somewhere. This includes regions where cosmic inflation ended slightly earlier or later, where dark matter clumped into different patterns, where the first generation of stars formed under varying circumstances, where galaxy formation proceeded along alternative pathways. Modern cosmological observations provide substantial support for the possibility of infinite space. The cosmic microwave background radiation, measured with exquisite precision by space-based telescopes, appears perfectly flat within observational margins of error. This flatness suggests that the universe's geometry extends indefinitely, rather than curving back on itself in a closed loop. The additional evidence comes from studies of distant supernovae, which confirm that space possesses the critical density necessary for flat geometry. Consider the practical implications of this infinite repetition for our understanding of rarity and probability. Events that seem impossibly unlikely in our finite experience become inevitable certainties across infinite space. The exact sequence of coin flips that led to your birth, the precise environmental conditions that allowed life to emerge on Earth, the specific evolutionary pathway that created human consciousness, all these seemingly miraculous coincidences repeat infinitely throughout space. This mathematical certainty extends to the most complex phenomena imaginable. Somewhere in infinite space exists a region where every molecule of air in your room spontaneously arranges itself into a perfect replica of Shakespeare's complete works, suspended in gaseous form for a brief moment before dispersing. While such an event has a probability so small as to be effectively impossible in our observable universe, infinite space guarantees its occurrence infinitely many times. The Level 1 multiverse also addresses fundamental questions about the apparent fine-tuning of physical constants. Our universe appears precisely calibrated to support complex structures like stars, planets, and life. The strength of gravity, the mass of electrons, the rate of cosmic expansion, all seem delicately balanced to permit the existence of atoms, chemistry, and biology. In a single finite universe, this fine-tuning might appear as an extraordinary coincidence requiring explanation. In infinite space with uniform physics, however, we naturally find ourselves in a region where conditions permit our existence, not because of design or extraordinary luck, but because we could not exist anywhere else to observe different conditions. The Level 1 multiverse ultimately transforms our understanding of existence itself, shifting our perspective from inhabitants of a single, finite cosmos to members of an infinite community of worlds. Every human achievement, every moment of beauty, every act of love and creativity repeats endlessly across space, creating connections that transcend the vast distances separating our cosmic twins. The night sky ceases to be merely a view of distant stars and becomes instead a window toward infinite possibility, where every point of light represents not just a single star, but a beacon in a vast ocean of space containing every conceivable world, every possible story, every potential future that mathematics allows. Level 2, Multiverse, Bubble Universes and Eternal Inflation. Beyond the infinite repetitions of the Level 1 multiverse lies an even more extraordinary realm of possibility. A cosmic landscape where entire universes exist as isolated bubbles in an ever-expanding sea of space-time. This is the Level 2 multiverse, where the very laws of physics themselves can vary from one cosmic domain to another, creating a collection of universes so diverse that our own reality represents just one possible way that existence can unfold. The foundation of the Level 2 multiverse rests on our understanding of cosmic inflation, the period of exponential expansion that occurred during the first tiny fraction of a second after the Big Bang. This inflationary epoch, though lasting only about 10 to the power of -32 seconds, expanded space by an enormous factor, stretching regions smaller than atomic nuclei to sizes larger than basketballs. This expansion smoothed out irregularities and created the remarkably uniform cosmos we observe today. But inflation theory suggests something far more profound than a single episode of expansion. According to the mathematics governing inflationary fields, once inflation begins in any region of space, it tends to continue indefinitely. This process, known as eternal inflation, creates a situation where some regions of space stop inflating and form what we recognize as universes, while other regions continue expanding at exponential rates. The result is an infinite collection of bubble universes, each separated from the others by vast oceans of eternally inflating space. Imagine a pot of boiling water, where bubbles continuously form and rise to the surface. Each bubble represents a universe like ours, complete with its own Big Bang, its own expansion history, and its own collection of galaxies, stars, and planets. The boiling water itself represents the eternally inflating space between these bubble universes, constantly creating new bubbles while existing ones drift apart from each other at ever-increasing speeds. The mathematics behind eternal inflation emerge from quantum field theory, where energy fields permeate all of space. During inflation, a field called the inflaton drove the exponential expansion. But quantum mechanics introduces fundamental uncertainty into this process. In some regions, quantum fluctuations cause the inflaton field to decay, ending inflation and creating a bubble universe. In other regions, the field continues to drive expansion, maintaining the inflationary state. This process resembles radioactive decay, but operating on cosmic scales. Just as radioactive atoms decay at random intervals, while the overall decay rate remains predictable, regions of inflating space randomly transition to non-inflating states, while the bulk of space continues expanding. The key difference is that inflating space grows faster than it decays, ensuring that the overall volume of inflating regions increases without bound. This guarantees the eternal production of new bubble universes. Each bubble universe begins with its own version of the Big Bang, when inflation ends in that particular region. The energy that previously drove inflation gets converted into the hot, dense state of matter and radiation that we associate with the early universe. From this point, each bubble evolves according to the same physical laws that govern our cosmos. Gravity shapes the formation of galaxies, nuclear fusion powers stars, and chemistry enables the emergence of complex structures. But here lies the truly remarkable aspect of the Level 2 multiverse. The fundamental constants and forces that govern each bubble universe can differ dramatically from our own. The strength of gravity, the masses of elementary particles, the number of spatial dimensions, even the basic forces that exist. All these fundamental properties can vary from bubble to bubble during the transition from the inflating to the non-inflating state. This variation occurs because the process that ends inflation involves the settling of quantum fields into their lowest energy states. Just as a ball rolling down a hill can settle into different valleys depending on the precise path it takes, the quantum fields that determine physical constants can settle into different configurations in different bubble universes. These configurations, known as vacuum states, determine the basic properties of matter, energy, and space-time within each bubble. In some bubbles, gravity might be thousands of times stronger than in our universe, causing stars to burn out in mere thousands of years instead of billions. In others, gravity could be so weak that matter never clumps together to form galaxies or stars at all. The electromagnetic force might be dramatically different, altering the behavior of atoms and making chemistry as we know it impossible. Some bubbles might contain entirely different types of particles, creating forms of matter that bear no resemblance to anything in our reality. The distances separating these bubble universes defy comprehension. While bubbles form continuously throughout the eternally inflating space, they drift apart from each other faster than light can travel between them. This doesn't violate relativity because it's space itself that expands, carrying the bubbles along like boats on a rapidly flowing river. Even if we could somehow travel at the speed of light, we would never catch up to neighboring bubbles because the space between us and them grows faster than we could traverse it. This eternal separation ensures that bubble universes remain forever isolated from each other. No information, matter, or energy can pass from one bubble to another. Each universe represents a completely self-contained reality, unaware of the existence of countless other realities floating in the same cosmic sea. Our observable universe, stretching 46 billion light-years in every direction, represents just a tiny portion of our particular bubble, which itself is just one among infinite bubbles in the eternal multiverse. The Level 2 Multiverse provides a natural explanation for what appears to be the fine-tuning of physical constants in our universe. Many fundamental properties of our cosmos seem precisely calibrated to allow the existence of complex structures like stars, planets, and life. Change the strength of the nuclear forces by even a small percentage, and stars would either burn out too quickly or never ignite at all. Alter the mass of electrons slightly, and atoms couldn't form stable molecules. In a universe with fixed physical constants, such precise calibration might seem to require explanation, perhaps suggesting design or extraordinary coincidence. But in the Level 2 multiverse, every possible combination of physical constants exists somewhere among the infinite bubbles. We naturally find ourselves in a bubble where conditions permit our existence because we couldn't exist in bubbles with different constants to observe them. This selection effect, known as the anthropic principle, transforms apparent fine-tuning from a mysterious coincidence into an inevitable consequence of infinite cosmic diversity. The implications extend beyond just explaining fine-tuning. The Level II Multiverse suggests that reality encompasses every possible way that physics can be configured. Bubbles exist where the strong nuclear force is stronger, creating different types of atomic nuclei and enabling entirely different forms of chemistry. Other bubbles might have extraspatial dimensions, allowing for exotic geometries and gravitational effects unknown in our three-dimensional space. Some bubbles might even contain different numbers of fundamental forces. While our universe operates through four basic interactions: gravity, electromagnetism, and the strong and weak nuclear forces, other bubbles might combine these forces differently or contain entirely new types of interactions. The possibilities are truly limitless, constrained only by the mathematical structures that can emerge from the underlying quantum field dynamics. The Level II Multiverse also addresses questions about the ultimate fate of our universe. Current observations suggest that our cosmos will continue expanding forever, with galaxies drifting apart until stars burn out and black holes evaporate, leaving behind a cold, empty void. But in the broader context of eternal inflation, our bubble represents just one episode in an endless story of cosmic creation. While our particular universe may face heat death, new bubbles continue forming throughout the eternally inflating space, ensuring that cosmic evolution and the potential for complexity never truly end. This perspective transforms our understanding of cosmic significance. Rather than inhabiting a single, unique universe that will eventually fade into darkness, we exist within an infinite collection of realities where every possible story unfolds. Our bubble universe, with its particular combination of physical laws and cosmic history, represents one voice in an eternal chorus of existence, each bubble contributing its own unique melody to the infinite symphony of the Level II Multiverse. The eternal nature of this process means that creation never stops. Even as you read these words, countless new bubble universes are forming throughout the inflating space beyond our cosmic horizon. Each new bubble begins its own journey from a hot, dense Big Bang state toward whatever future its particular physical constants make possible. Some will develop complex chemistry and biology, others will remain forever barren, but all will add their own chapter to the endless story of existence in the Level II Multiverse. Level III Multiverse, Quantum Worlds and the Many Worlds. Interpretation. In the quantum realm, where particles exist in multiple states simultaneously, and reality becomes a tapestry of probabilities, lies perhaps the most profound multiverse of all. The Level III Multiverse emerges from the very foundations of quantum mechanics, suggesting that every quantum measurement, every random decay, every subatomic interaction creates new branches of reality. In this quantum multiverse, nothing is truly random. Instead, everything happens, each possibility playing out in its own parallel world. The story begins with one of the most puzzling aspects of quantum mechanics: the measurement problem. When scientists observe quantum particles, they find them in the definite states. An electron spins either up or down, a photon passes through either one slit or another. Yet, before measurement, quantum theory describes these particles as existing in superposition, simultaneously occupying all possible states with different probabilities. The mathematics works perfectly, but it leaves a fundamental question unanswered. What happens to all those other possibilities when we make a measurement? Traditional interpretations of quantum mechanics, known as the Copenhagen interpretation, suggest that measurement causes the wave function to collapse. All the potential realities except one simply vanish, leaving behind the single outcome we observe. But this explanation has always felt unsatisfying to many physicists. Why should observation have such a special role in determining reality? What mechanism causes this collapse? And what happens to all that information about other possible outcomes? In 1957, physicist Hugh Everett proposed a radical alternative that eliminates the need for wave function collapse entirely. Instead of other possibilities vanishing during measurement, Everett suggested that they all remain equally real. Every quantum measurement splits reality into multiple branches, each containing one possible outcome. the observer splits along with reality, creating multiple versions of themselves, each experiencing one particular result, while remaining unaware of the others. This many worlds interpretation transforms our understanding of quantum mechanics from a theory about probabilities into a theory about parallel realities. When a quantum particle faces a choice between spinning up or down, reality branches into two parallel worlds. In one branch, the particle spins up, and that version of you observes the up result. In the other branch, the particle spins down, and another version of you observes the down result. Both outcomes are equally real, equally valid, and equally experienced by the respective versions of you in each branch. The branching occurs continuously throughout the universe. Every quantum interaction, from the radioactive decay of atomic nuclei to the absorption of photons by your retina, creates new splits in reality. The rate of branching is astronomical. Countless quantum events occur every instant in every cubic centimeter of space, each one potentially creating new parallel worlds. Within a single second, reality branches into more parallel universes than there are atoms in the observable cosmos. Consider the implications for your personal experience. Right now, as photons from your environment interact with the quantum systems in your brain, reality is branching into countless versions. In some branches, you'll continue reading this sentence without interruption. In others, you might be distracted by a sound, a thought, or a decision to look away. Each possibility creates its own branch of reality, its own version of you experiencing that particular outcome. The quantum branching process preserves all information perfectly, unlike the Copenhagen interpretation, where unmeasured possibilities simply disappear. The many worlds model maintains every quantum state in its respective branch. Nothing is ever lost. Every possibility that quantum mechanics allows becomes reality somewhere in the branching multiverse. This conservation of quantum information resolves many puzzles about measurement, while creating a picture of reality far richer and stranger than everyday experience suggests. The mathematics underlying this interpretation relies on the concept of quantum decoherence. When quantum systems interact with their environment, their wave functions become entangled with the environmental degrees of freedom. This entanglement effectively separates different quantum possibilities into distinct branches that can no longer interfere with each other. The branches become isolated, allowing each one to evolve independently while maintaining internal consistency. Decoherence explains why we don't observe quantum superposition in everyday life. Large objects constantly interact with their environment through countless quantum exchanges, photons bouncing off surfaces, air molecules colliding with objects, thermal fluctuations affecting molecular motion. These interactions rapidly decohere any quantum superposition, effectively splitting reality into branches where objects occupy definite positions and states. Within each branch, classical physics emerges as an approximation of the underlying quantum reality. The Level III Multiverse contains every possible quantum history of our universe. Branches exist where the asteroid that killed the dinosaurs missed Earth, where key mutations in evolution occurred differently, where quantum fluctuations in the early universe led to alternative patterns of galaxy formation. But unlike the Level 1 and Level 2 multiverses, which involve different regions of space or different physical constants, the Level 3 Multiverse consists of different quantum outcomes within the same fundamental physical framework. This quantum multiverse addresses the apparent randomness we observe in quantum measurements. When you flip a quantum coin, you don't get a random result. You get both results, each in its own branch of reality. The randomness we perceive reflects our ignorance about which branch we'll find ourselves in after the measurement. From within any single branch, the outcome appears random because each version of you has access only to their particular branch's history. The branching structure creates a vast tree of parallel realities, with each branch splitting into multiple sub-branches as quantum events unfold. Early branches, corresponding to quantum events that occurred billions of years ago, have diverged dramatically from each other. More recent branches remain relatively similar, differing only in the outcomes of quantum events that have occurred since they separated. This creates a hierarchy of similarity among parallel worlds, with closer branches being more alike than distant ones. Personal identity becomes a complex concept in the quantum multiverse. Which version of you is the real you? The many worlds interpretation suggests that all versions are equally real and equally valid. You are not a single unique individual, but rather what philosophers call a person stage, one moment in the existence of one particular branch of yourself. Your sense of continuous identity comes from the fact that each branch preserves the memory and physical structure of its version of you, creating subjective continuity within each world, while objective branching occurs between them. The quantum multiverse also provides new perspectives on decision-making and free will. When you face a choice, quantum events in your brain may influence your decision-making process. If so, reality branches to accommodate all possible choices you might make. This doesn't eliminate free will, but rather suggests that all your possible choices are realized. Each version of you makes the decision that seems right from their perspective, based on the quantum processes occurring in their particular branch. Some branches of the quantum multiverse contain remarkable coincidences and unlikely events. In rare branches, quantum tunneling might cause all the air molecules in a room to spontaneously gather in one corner, or radioactive decay might arrange itself to spell out messages. While such events have vanishingly small probabilities in any given branch, the infinite branching of the quantum multiverse ensures they occur in some branches. These branches remain as real as any others, though they represent only tiny fractions of the total branching structure. The Level III Multiverse raises profound questions about the nature of probability and prediction. If all possible outcomes occur in some branch, what meaning do quantum probabilities have? The answer lies in the relative measure, or thickness, of different branches. Outcomes with higher quantum probabilities correspond to larger numbers of similar branches, while unlikely outcomes correspond to fewer branches. When making predictions, we're essentially estimating which type of branch we're more likely to find ourselves in. This quantum branching continues into the future, creating multiple potential destinies for yourself, humanity, and the universe. Branches exist where scientific breakthroughs occur at different times, where civilizations develop along alternative pathways, where cosmic events unfold in countless variations. Every possible future that quantum mechanics allows becomes reality in some branch of the multiverse, ensuring that the story of existence explores every conceivable path through the landscape of possibility. The many worlds interpretation transforms quantum mechanics from a theory about what might happen into a theory about what does happen. Everything that can happen does happen, each in its own parallel reality. This quantum multiverse reveals a cosmos where every moment branches into infinite possibilities, where every choice creates new worlds, and where the fundamental nature of reality is far stranger and more wonderful than the single world we directly experience. Level 4, Multiverse, mathematical structures as reality. At the deepest level of existence lies a multiverse so abstract and profound that it challenges our most fundamental assumptions about the nature of reality itself. The Level 4 Multiverse suggests that every mathematically coherent structure exists as a physical universe, transforming mathematics from a tool we use to describe reality into the very essence of reality itself. In this ultimate multiverse, our cosmos becomes just one possible mathematical arrangement among an infinite collection of all logically possible worlds. The foundation of this extraordinary concept rests on a deceptively simple observation. Mathematics seems to describe our universe with unreasonable effectiveness. The orbits of planets follow precise mathematical curves called ellipses. Light behaves according to mathematical equations that govern electromagnetic fields. Quantum mechanics operates through mathematical structures known as Hilbert spaces. Even the most exotic phenomena in physics, from black holes to the expansion of space itself, yield to mathematical description with remarkable precision. This effectiveness raises a profound question that has puzzled philosophers and physicists for centuries. Why should mathematics work so well in describing physical reality? One possible answer is that mathematics doesn't merely describe reality. Mathematics is reality. This radical proposition, known as the mathematical universe hypothesis, suggests that our physical universe is literally a mathematical structure, existing not because it's made of some fundamental substance, but because it represents a self-consistent set of mathematical relationships. To understand this concept, consider what we mean when we refer to physical objects. A proton isn't truly a tiny ball of matter, but rather a set of relationships between quantum fields. An electron isn't a particle with definite properties, but a solution to mathematical equations that describe its behavior in various circumstances. Even space and time emerge from mathematical structures in theories like general relativity, where the geometry of space-time becomes the fundamental reality underlying gravitational phenomena. If our universe is indeed a mathematical structure, then the level 4 multiverse follows naturally. Mathematics contains countless different structures, geometries with different numbers of dimensions, algebraic systems with different operations, logical frameworks with different rules. If mathematical existence is equivalent to physical existence, then every self-consistent mathematical structure must correspond to some form of reality. Our universe becomes just one mathematical structure among infinite others. The diversity of mathematical structures is truly staggering. Consider geometries alone. We're familiar with the three-dimensional Euclidean space of everyday experience, but mathematics describes spaces with any number of dimensions, from zero-dimensional points to infinite-dimensional function spaces. Some spaces curve positively like spheres, others curve negatively like saddles, and still others twist and fold in ways that defy visualization. In the level 4 multiverse, each of these geometric structures corresponds to a universe with its own unique spatial properties. Beyond geometry, like countless other mathematical frameworks, group theory describes symmetries and transformations. Number theory explores the properties of integers and their relationships. Category theory provides abstract structures for organizing mathematical concepts themselves. Each branch of mathematics contains numerous specific structures, and in the level 4 multiverse, each structure represents a possible universe with its own internal logic and consistency. Some of these mathematical universes would be utterly alien to our experience. Imagine a universe based on discrete mathematics, where space and time come in indivisible chunks rather than flowing continuously. Such a universe might resemble a vast cellular automaton, with reality updating in discrete steps according to the fixed rules. Entities in such a universe would experience existence as a series of discrete moments, each following inevitably from the previous according to the mathematical rules governing their reality. Other universes might be based on non-commutative mathematics, where the order of operations matters in fundamental ways. In our universe, moving 3 steps north, then 2 steps east, gets you to the same place as moving 2 steps east, then 3 steps north. But in a non-commutative universe, the order of these operations could yield different results, creating a reality where the sequence of events affects outcomes in ways that seem impossible from our perspective. The level 4 multiverse includes universes with different logical foundations. While our reality appears to operate according to classical logic, where statements are either true or false, mathematical logic encompasses many alternative systems. Fuzzy logic allows for the degrees of truth between absolute true and false. Quantum logic reflects the strange behavior of quantum systems, where classical logical rules sometimes break down. In the level 4 multiverse, each logical system corresponds to universes where reality operates according to different rules of truth and consistency. Time itself becomes variable across different mathematical structures. Some universes might have multiple time dimensions, creating realities where causality operates along several independent temporal axes. Others might have circular time, where effects can precede their causes, or branching time that splits and merges according to mathematical rules. Still others might exist outside of time entirely, representing eternal mathematical structures, where all relationships exist simultaneously without temporal sequence. The concept of observers and consciousness becomes particularly intriguing in the level 4 multiverse. If every mathematical structure corresponds to a universe, then some structures must contain patterns complex enough to process information and exhibit what we might recognize as consciousness. These conscious patterns would experience their mathematical universe from within, just as we experience our mathematical structure from our internal perspective. But consciousness itself might take radically different forms across different mathematical structures. In universes based on discrete mathematics, consciousness might operate through digital-like processes, fundamentally different from the analog processes of biological brains. In higher dimensional universes, conscious entities might perceive and process information in ways that utilize additional spatial dimensions we cannot imagine. The diversity of possible conscious experiences across mathematical structures could encompass forms of awareness utterly unlike anything in our reality. The Level 4. Multiverse provides the most complete answer possible to questions about fine-tuning and the apparent specialness of our universe. Rather than asking why our physical constants have the values they do, we can recognize that all possible values exist somewhere in the mathematical multiverse. We find ourselves in a universe with these particular constants not because they're special, but because we can only exist in mathematical structures that permit our form of complexity and consciousness. This ultimate multiverse also addresses questions about the origin of existence itself. Rather than asking why something exists rather than nothing, the Level 4 multiverse suggests that the question is meaningless. Mathematical structures don't come into existence. They simply are, in the same sense that the number 7 or the concept of a circle simply exist within mathematics. Our universe doesn't require creation or a beginning, because it represents an eternal mathematical truth that exists independently of time or causation. The boundaries between different universes in the Level 4 multiverse are absolute. Unlike other multiverse levels, where universes exist in the same mathematical framework but in different regions or branches, Level 4 universes are separated by the fundamental incompatibility of their mathematical structures. No information or influence can pass between universes based on different mathematical foundations because they share no common framework for interaction. Yet, despite this absolute separation, the Level 4 multiverse creates a profound sense of connection across all possible realities. Every mathematical structure that can exist does exist, meaning that reality encompasses every possible way that existence can be organized. Our universe, with its particular mathematical foundation, contributes one voice to an infinite chorus of mathematical realities, each exploring its own unique possibilities within the vast landscape of logical possibility. The Level 4 multiverse represents the ultimate democratization of existence. No mathematical structure is more real or fundamental than any other. Each exists with equal validity within the realm of mathematical truth. Our familiar three-dimensional space, with its particular physical laws, becomes just one arrangement among infinite others, neither special nor unique except from our necessarily limited internal perspective. In this deepest of all multiverses, mathematics ceases to be an abstract human invention and reveals itself as the fundamental nature of reality itself. Every equation, every geometric structure, every logical system corresponds to some form of existence, creating a multiverse where every possible way of being finds expression in the infinite landscape of mathematical truth. Brane Worlds, universes, floating in higher dimensions. In the deepest theories of modern physics lies a vision of reality so profound that it transforms our entire understanding of the cosmos. String theory suggests that our familiar three-dimensional universe is not the complete picture, but rather a thin slice of existence floating within a vast ocean of higher dimensional space. These theoretical constructs, known as branes, short for membranes, propose that our entire observable universe exists as a three-dimensional surface embedded in dimensions we cannot directly perceive or access. To understand this remarkable concept, imagine a sheet of paper floating in a room. From the perspective of a two-dimensional being living on that paper, their entire universe consists of length and width. They cannot perceive the third dimension that surrounds their flat world, yet that dimension profoundly influences their reality. Similarly, string theory suggests that our three-dimensional space might be a brane floating in a higher dimensional bulk space, with additional dimensions curled up or extended in ways our senses cannot detect. The mathematics of string theory requires extra dimensions beyond the four we experience, 3 of space and 1 of time. These theories typically invoke 10 or 11 total dimensions, with 6 or 7 dimensions beyond our familiar 4 somehow hidden from direct observation. These extra dimensions might be compactified, curled up into structures so small that their effects remain invisible at the scales we can measure. Alternatively, we might be confined to our three-dimensional brain, unable to travel into the additional dimensions that surround us. In this Brane Worlds scenario, the fundamental particles and forces we observe are not free to move through all dimensions of space. Instead, they are trapped on our three-dimensional brain, like insects crawling on the surface of a balloon. The particles that make up atoms, the electromagnetic forces that bind molecules, and even the nuclear forces that power stars are all confined to our brain, creating the rich complexity of chemistry and biology within this three-dimensional prison. However, gravity behaves differently in Brane World models. Unlike other forces, gravity might propagate through the higher dimensional bulk space, spreading its influence across all dimensions rather than being confined to our brain. This could explain why gravity appears so much weaker than other fundamental forces. When we observe gravitational attraction between objects on our brain, we might be seeing only a small fraction of gravity's total strength, with most of its influence diluted across the higher dimensions we cannot access. The weakness of gravity has puzzled physicists for decades. Electromagnetic forces can lift a paperclip against the gravitational pull of the entire Earth, suggesting that gravity is extraordinarily weak compared to other fundamental interactions. In Brane World models, this weakness results from gravity's ability to spread into extra dimensions, like sound from a speaker that becomes quieter as it spreads through three-dimensional space. Gravity becomes weaker as it disperses through higher dimensional bulk space, leaving only a faint echo on our three-dimensional brain. Multiple brains can coexist within the same higher dimensional space, separated by distances measured in these extra dimensions. Each brain could harbor its own universe, complete with its own physics, particles, and potentially its own forms of matter and energy. These parallel universes would exist nearby in higher dimensional space, yet remain completely inaccessible to us because we cannot travel through the dimensions that separate us from them. The spacing between brains introduces fascinating possibilities for interaction. If brains drift close together in higher dimensional space, gravity from one brain might influence matter on another. This could manifest as mysterious dark matter in our universe, gravitational effects from particles living on a nearby brain, invisible to us because light and other electromagnetic radiation cannot cross the dimensional gap between brains. Some models suggest that our brain oscillates or vibrates within the higher dimensional space, like a drumhead resonating in air. These vibrations could create waves that propagate through the bulk space, potentially carrying information or energy between different regions of our brain, or even between different brains. The detection of such gravitational waves might provide the first direct evidence for the extra dimensions predicted by string theory. Brane World cosmology offers elegant explanations for the origin and evolution of our universe. In some scenarios, the Big Bang represents a collision between two brains moving through higher dimensional space. When brains collide, the enormous energies involved could create the hot, dense conditions that gave birth to our observable universe. The expansion of space that we observe might reflect the aftermath of this collision, as our brain rebounds and separates from its collision partner. This collision scenario provides a natural mechanism for the Cyclic Universe models. After expanding apart following their collision, two brains might eventually be drawn back together by gravitational attraction, operating through the higher dimensions. Another collision would trigger a new cycle of cosmic expansion, creating an eternally repeating sequence of universal births and rebirths. Our current universe might be just one cycle in an infinite series of brain collisions, stretching infinitely into the past and future. The geometry of higher dimensional space itself influences the physics we observe on our brain. Different shapes and curvatures in the extra dimensions create different patterns of particle behavior and force interactions. A universe on a brain embedded in one geometric configuration might exhibit different physical constants than a universe on a brain in differently curved higher dimensional space. This geometric variation could explain the apparent fine-tuning of physical constants in our universe. We observe these particular values because they result from the specific geometric arrangement of our brain within the higher dimensional bulk. Brane Worlds also provide new perspectives on quantum mechanics and the nature of reality. Quantum field fluctuations might extend into the extra dimensions, creating correlations between events on our brain and processes occurring in the higher dimensional bulk. These correlations could influence quantum measurements in subtle ways, potentially affecting the probabilities we observe for different quantum outcomes. The concept of information becomes particularly intriguing in Brane Worlds scenarios. While matter and electromagnetic radiation remain trapped on our brain, information might find ways to propagate through higher dimensions. Quantum entanglement between particles on our brain might reflect deeper connections that extend through the extra dimensions, creating non-local correlations that transcend the apparent limitations of three-dimensional space. Black holes take on new properties in Brane world models. When matter on our brain collapses to form a black hole, the gravitational effects extend into the higher dimensional bulk space. This creates higher dimensional black holes that might behave very differently from their three-dimensional counterparts. Information falling into such black holes might escape into the extra dimensions, potentially resolving the information paradox that has puzzled physicists studying black hole thermodynamics. The search for experimental evidence of extra dimensions focuses on deviations from Newton's law of gravitation at very small scales. If gravity can spread into extra dimensions, its strength should deviate from the inverse square law when measured at distances comparable to the size of the compactified dimensions. Precision experiments that measure gravitational forces between small objects at microscopic separations might reveal the signature of higher dimensional space. Particle accelerator experiments also search for evidence of extra dimensions through the production of particles that could escape into the higher dimensional bulk. If such particles exist, they would appear as missing energy in collision experiments, carried away by particles that vanish from our three-dimensional perspective when they enter the extra dimensions. The Large Hadron Collider and other high-energy experiments continue to search for these dimensional escape signatures. The Brane world picture transforms our understanding of cosmic isolation. Rather than existing in a vast, mostly empty three-dimensional space, our universe becomes one layer in a rich, multi-dimensional reality, filled with parallel branes hosting their own universes. We remain forever separated from these other realities by the dimensional barriers that confine us to our particular brane, yet we share the same higher dimensional space that contains them all. The implications for consciousness and observation become profound in Brane world scenarios. If our thoughts and perceptions are confined to our three-dimensional brane, then our entire understanding of reality is necessarily limited by this dimensional imprisonment. We can theorize about higher dimensions and parallel branes, but we can never directly experience them. This creates a humbling perspective on the nature of knowledge itself. We might be like shadows cast on a wall, aware only of our flat projections, while the true three-dimensional objects that create us remain forever beyond our direct perception. Yet this limitation also reveals the remarkable achievement of human intelligence. Through mathematics and theoretical physics, minds confined to a three-dimensional brane have managed to envision and describe the higher dimensional reality that contains them. We have used the subtle effects of gravity and the elegant mathematics of string theory to peer beyond our dimensional boundaries, constructing detailed models of realms we can never visit. This vision of reality reveals the cosmos as far stranger and more magnificent than everyday experience suggests. Our familiar three-dimensional world, with all its complexity and beauty, represents just one surface in an infinite higher dimensional ocean, where countless other universes drift like leaves on the wind, each carrying its own unique story of existence through the vast landscape of higher dimensional space. The string landscape, 10 to the power of 500 ways to build a universe. Within the mathematical framework of string theory lies perhaps the most staggering concept in all of physics, a landscape of possible universes so vast that it defies human comprehension. This string landscape contains not millions, not billions, but approximately 10 to the power of 500 different ways to construct a universe, each representing a unique set of physical laws, particle properties, and fundamental constants. To put this number in perspective, the total number of atoms in the observable universe is merely 10 to the power of 80. The string landscape dwarfs even this cosmic inventory by an almost unimaginable margin. The foundation of this incredible diversity lies in the extra dimensions that string theory requires. While we experience 3 dimensions of space and 1 of time, string theory operates in 10 or 11 total dimensions. The additional 6 or 7 dimensions must be compactified, curled up into tiny geometric structures that remain hidden from our direct observation. These compactified dimensions take the form of complex mathematical objects called Calabi-Yau manifolds, named after the mathematicians who first studied their intricate properties. Each Calabi-Yau manifold represents a different way to curl up the extra dimensions, and each different configuration produces a universe with distinct physical properties. The geometry of these hidden dimensions determines the masses of particles, the strengths of fundamental forces, and even which particles can exist at all. A universe built on one Calabi-Yau manifold might contain electrons with different masses than our own, while a universe based on another manifold might lack electrons entirely, replacing them with exotic particles that follow different quantum mechanical rules. The number of possible Calabi-Yau manifolds is truly astronomical. Mathematicians have identified thousands of distinct types, each with its own unique geometric properties. But the complexity extends far beyond the basic manifold structure. Each manifold can be modified through additional geometric features, holes, handles, and twisted connections that further alter the physics they produce. The manifolds can also support different field configurations, patterns of energy and flux, that thread through their geometric structure like magnetic field lines through space. These field configurations, known as flux compactifications, add another layer of complexity to the string landscape. Magnetic and electric flux can wind around the various cycles and surfaces within a Calabi-Yau manifold, creating different patterns that affect the resulting physics. Each possible pattern of flux threading through a manifold creates a different vacuum state, a different ground-level configuration of the universe's fundamental fields. The number of these vacuum states quickly multiplies into the hundreds of thousands for even relatively simple manifolds. When mathematicians and physicists attempted to count all possible combinations of manifold types, geometric modifications, and flux configurations, they discovered that the total number of distinct vacuum states reaches approximately 10 to the power of 500. This incomprehensibly large number represents the full scope of the string landscape, every possible way that string theory can construct a universe with different physical laws and properties. Each point in this vast landscape corresponds to a universe with its own unique characteristics. In some regions of the landscape, gravity might be much stronger than in our universe, causing stars to burn out quickly and preventing the formation of stable planetary systems. Other regions might feature additional fundamental forces beyond the 4 we know, creating complex interactions between particles that could produce entirely novel forms of matter and energy. The masses of particles vary dramatically across the string landscape. In our universe, the electron has a specific mass that allows atoms to form stable structures suitable for chemistry and biology. But in other regions of the landscape, electrons might be much heavier or much lighter, fundamentally altering the nature of atomic structure. Some universes might lack certain particles entirely, while containing others that have no counterpart in our reality. The fundamental constants that govern physical interactions, the speed of light, the strength of electromagnetic force, the rate of quantum mechanical processes, all depend on the specific point in the string landscape where a universe finds itself. These constants appear finely tuned in our universe, taking values that allow for the existence of stars, planets, and complex chemistry. The string landscape reveals that these values are not inevitable or unique, but represent just one possibility among an almost infinite array of alternatives. Most regions of the string landscape produce universes that would be utterly hostile to any form of complexity or life as we understand it. Universes where forces are too strong might prevent atoms from forming, while universes where forces are too weak might allow matter to disperse without ever condensing into stars and galaxies. The vast majority of possible universes in the string landscape would be empty, lifeless expanses where no interesting structures could ever develop. This realization provides a natural explanation for the apparent fine-tuning of physical constants in our observable universe. Rather than requiring some special mechanism to set the constants at precisely the right values, the string landscape suggests that all possible values exist somewhere within the vast collection of universes. We find ourselves in a universe with these particular values, not because they are special or designed, but because only universes with suitable constants can produce observers capable of asking questions about their existence. The string landscape operates through a process analogous to biological evolution, but on a cosmic scale. Universes with certain properties might be more likely to reproduce or spawn new universes, creating a selection pressure that favors certain regions of the landscape. This cosmic evolution could explain why we observe the particular combination of physical laws and constants that characterize our reality. Different mechanisms might drive this cosmic evolution. Universes that produce black holes might spawn baby universes through quantum processes occurring at the black hole singularities. Universes that undergo eternal inflation might continuously create new regions of spacetime, each potentially settling into different vacuum states. Through such processes, successful universe configurations might become more common over cosmic timescales, creating an evolutionary pressure toward universes capable of complexity and self-reproduction. The transitions between different regions of the string landscape occur through quantum tunneling events that can change the vacuum state of space itself. These transitions are extraordinarily rare, typically taking times much longer than the current age of our universe. However, in regions undergoing eternal inflation, the rapid expansion of space creates countless opportunities for such transitions to occur, allowing the exploration of many different vacuum states within the same cosmic structure. The anthropic principle finds its most natural expression within the context of the string landscape. This principle suggests that we observe particular physical constants not because they are fundamentally special, but because only universes with these constants can produce observers. The string landscape provides the vast ensemble of universes necessary for the anthropic principle to operate. Among 10 to the power of 500 different possibilities, it becomes natural that some universes would have the right properties for complexity in life. Eternal inflation combined with the string landscape creates what cosmologists call the multiverse, a vast collection of regions, each corresponding to different points in the landscape and thus exhibiting different physical laws. Our observable universe represents just one such region, where the fields have settled into a particular vacuum state that produces the physics we observe. Other regions, perhaps separated from us by vast distances or existing in parallel dimensions, explore different possibilities from the string landscape. The implications for fundamental physics are profound. Rather than seeking a unique theory that predicts the specific values of physical constants we observe, physicists might need to accept that these values are environmental, determined by which region of the string landscape our local universe happens to occupy. This shifts the focus from explaining why our constants have their particular values to understanding the overall structure of the landscape and the processes that determine which regions are most commonly realized. Experimental verification of the string landscape presents enormous challenges. The different vacuum states typically differ in ways that would be observable only at energy scales far beyond what current particle accelerators can achieve. However, subtle effects might be detectable through precision measurements of particle properties or through cosmological observations that reveal signatures of transitions between different vacuum states in the early universe. The string landscape transforms our understanding of naturalness in physics. Rather than expecting physical constants to take the most natural or simple values, the landscape suggests that we should expect to find ourselves in regions where the constants take whatever values are necessary for the existence of observers. This anthropic perspective on naturalness provides a completely different framework for understanding why our universe appears so precisely balanced for the existence of complexity. Within this vast landscape of possibilities, our familiar universe becomes just one note in an infinite symphony of realities. Each possible configuration of extra dimensions creates its own unique harmony of physical laws, most producing only silence where no observers could ever emerge to appreciate their mathematical beauty. Yet among all these possibilities, some few universes develop the precise conditions necessary for matter to organize itself into patterns complex enough to contemplate the very landscape that gave them birth. The string landscape reveals the cosmos as a vast space of possibilities, where every conceivable way of organizing the fundamental forces and particles finds expression somewhere within its infinite expanse. Our universe, with its particular laws and constants, represents just one path through this landscape, a path that happened to lead to stars, planets, and eventually to minds capable of discovering the remarkable theoretical framework that encompasses all possible worlds. Quantum decoherence, the separation of realities. In the quantum realm, where particles exist in multiple states simultaneously, and reality becomes a dance of probabilities, lies one of the most elegant solutions to the deepest puzzles of quantum mechanics. Quantum decoherence reveals that the parallel worlds suggested by quantum theory don't disappear through some mysterious collapse. Instead, they gradually separate from each other, becoming isolated branches of reality that can no longer interfere or communicate. This gentle branching process explains why we experience a single, definite world, despite living in a fundamentally quantum universe where all possibilities coexist. The story of decoherence begins with the central mystery of quantum measurement. When scientists observe quantum particles in the laboratory, they always find them in definite states, an electron spinning either up or down, a photon passing through either one slit or another in a double-slit experiment. Yet quantum theory describes these particles as existing in superposition before measurement, simultaneously occupying all possible states with different probabilities assigned to each possibility. This creates a profound puzzle known as the measurement problem. If quantum particles exist in superposition, why do we never observe superposed states directly? Why does the act of measurement seem to force quantum systems to choose one definite outcome from among all their possibilities? Traditional interpretation suggested that observation causes the quantum wave function to collapse, instantly eliminating all possibilities except the one we observe. But this explanation raised more questions than it answered, requiring some special, undefined mechanism that could distinguish measurement from other physical interactions. Decoherence theory provides a more natural explanation by examining what happens when quantum systems interact with their environment. Every quantum system, no matter how carefully isolated, inevitably exchanges information with its surroundings through countless microscopic interactions. Photons bounce off surfaces, air molecules collide with objects, thermal fluctuations affect molecular motion, and electromagnetic fields permeate space. These environmental interactions don't destroy quantum superposition. Instead, they entangle the quantum system with its environment in ways that effectively separate different quantum possibilities into isolated branches. To understand this process, imagine a quantum particle that exists in a superposition of two different positions. Initially, the particle's wave function describes both positions simultaneously, and these different possibilities can interfere with each other, creating the strange quantum effects we observe in carefully controlled experiments. However, as soon as the environment begins to interact with the particle, the situation changes dramatically. Photons from the surrounding environment scatter off the particle differently depending on which position it occupies. Air molecules collide with the particle in ways that depend on its location. These interactions create entanglement between the particle and the environmental degrees of freedom. The quantum states of the photons, air molecules, and other environmental systems become correlated with the particle's position. This entanglement doesn't collapse the superposition, but rather spreads it into the environment. As this entanglement develops, the different branches of the quantum superposition become embedded in increasingly different environmental states. The branch where the particle is in position A becomes entangled with environmental configurations that record this information. Scattered photons carry away evidence of the particle being at position A, while displaced air molecules preserve traces of the particle's presence there. Meanwhile, the branch where the particle is in position B becomes entangled with different environmental configurations that record that alternative reality. The crucial insight of decoherence theory is that these entangled environmental states become extremely difficult to bring back together. The environment consists of countless degrees of freedom, vast numbers of photons, molecules, and field fluctuations that have interacted with the quantum system. Reversing all these interactions to restore the original superposition would require precise control over every environmental degree of freedom, a practical impossibility given the astronomical number of particles involved. This irreversible spreading of quantum information into the environment creates effective classical behavior without requiring any fundamental change to quantum mechanics. The different branches of the superposition still exist, but they can no longer interfere with each other because they are embedded in orthogonal environmental states. From the perspective of any observer within one branch, the other branches become inaccessible and undetectable, creating the appearance of a single, definite reality. The timescales for decoherence vary dramatically depending on the system and its environment. For microscopic quantum systems in carefully controlled laboratory conditions, decoherence might take microseconds or milliseconds, allowing scientists to observe quantum interference effects before the environment destroys them. For larger objects interacting with room temperature environments, decoherence occurs almost instantaneously, within tiny fractions of a second, far too quickly for quantum effects to be observable. This explains why we don't see quantum superposition in everyday life. A baseball exists in a definite position, not because quantum mechanics fails at large scales, but because the countless environmental interactions that affect the baseball cause its position to decohere almost instantaneously. The quantum superposition of different baseball positions spreads into the environment so quickly that we never have a chance to observe the quantum interference effects that would reveal the underlying superposition. Decoherence operates through the fundamental physics of information and entropy. When a quantum system interacts with its environment, information about the system's state spreads into the environmental degrees of freedom. This information becomes distributed among so many environmental particles that retrieving it becomes practically impossible. The process increases the total entropy of the system plus environment, making the separation of quantum branches thermodynamically irreversible. The environment doesn't need to be observed or measured to cause decoherence. The mere fact that environmental systems become entangled with the quantum system is sufficient to separate the different branches. This resolves one of the major conceptual problems with collapse interpretations of quantum mechanics. Decoherence doesn't require any special role for conscious observers or measurement apparatus. The environment itself provides the mechanism that creates apparent classical behavior from underlying quantum processes. Different types of environmental interactions lead to decoherence at different rates and in different ways. Electromagnetic interactions typically cause the fastest decoherence for charged particles, as photons readily carry away information about particle positions and states. Gravitational interactions cause much slower decoherence but affect all forms of matter universally. Thermal interactions with surrounding matter create decoherence through molecular collisions and energy exchanges. The process of decoherence is selective, affecting different quantum properties at different rates. Position typically decoheres much faster than internal quantum states like spin, because position couples more strongly to environmental interactions. This selectivity explains why some quantum properties persist longer than others in noisy environments, allowing for the possibility of quantum technologies that exploit the more robust quantum states while accepting decoherence in others. Decoherence theory provides a natural framework for understanding the emergence of classical physics from quantum mechanics. Rather than requiring a fundamental distinction between quantum and classical realms, decoherence shows how classical behavior emerges when quantum systems become sufficiently entangled with their environments. The classical world we experience represents the limit where decoherence has proceeded so thoroughly that quantum interference effects become unobservable. This perspective transforms our understanding of the relationship between microscopic and macroscopic physics. The laws of quantum mechanics remain universal, governing everything from elementary particles to astronomical objects. However, the effects of environmental entanglement create different phenomenology at different scales. Microscopic systems in isolated conditions can maintain quantum coherence and exhibit interference effects, while macroscopic systems in complex environments rapidly decohere and exhibit classical behavior. The many-worlds interpretation of quantum mechanics finds natural support from decoherence theory. Rather than requiring mysterious wave function collapse, decoherence explains how the different branches of quantum superposition become separated into parallel realities. Each branch corresponds to a different pattern of environmental entanglement, and observers within each branch experience a consistent classical reality while remaining unaware of the other branches. In this view, measurement doesn't create reality, but rather determines which branch of reality an observer finds themselves experiencing. The quantum measurement process separates an observer into multiple branches, each embedded in environmental states that preserve the record of one particular measurement outcome. All outcomes occur in the branching quantum multiverse, but decoherence ensures that observers in each branch experience only their local branch's history. Decoherence also illuminates the nature of quantum information and its relationship to classical information. Quantum information can exist in superposition and exhibit non-local correlations, but when this information becomes entangled with environmental degrees of freedom, it transforms into classical information distributed throughout the environment. This transformation is irreversible under normal circumstances, creating an arrow of time for information processing that parallels the thermodynamic arrow of time. The study of decoherence has practical implications for quantum technologies. Understanding how different environmental factors cause decoherence allows engineers to design better quantum computers, quantum communication systems, and quantum sensors. By identifying and controlling the dominant sources of decoherence, researchers can extend the coherence times of quantum systems and improve the performance of quantum devices. Modern experiments can observe decoherence in real time by monitoring quantum systems as they interact with controlled environments. These studies reveal the detailed mechanisms by which quantum coherence is lost and provide precise tests of decoherence theory predictions. Such experiments have confirmed that decoherence proceeds exactly as the theory predicts, providing strong support for this understanding of quantum measurement. Decoherence reveals the quantum universe as a constantly branching tree of realities, where every interaction with the environment creates new separations between parallel worlds. We inhabit one branch of this vast quantum multiverse, experiencing a single thread of consistency carved out by the environmental interactions that have shaped our particular history. The other branches continue to exist, carrying their own versions of reality forward through the endless dance of quantum possibility, forever separated from us by the gentle but inexorable process of decoherence. Superposition and splitting, Schrödinger's universe. In the heart of quantum mechanics lies a principle so fundamental, yet so counterintuitive, that it challenges our most basic assumptions about the nature of reality. Quantum superposition reveals that particles don't simply exist in one state or another. Instead, they exist in all possible states simultaneously, with each possibility contributing to the particle's complete description. This quantum multiplicity creates a universe where every potential outcome coexists until the moment of observation, when reality appears to choose one path while the others fade from our direct experience. The concept of superposition emerged from the early pioneers of quantum theory as they struggled to understand the bizarre behavior of atoms and subatomic particles. When scientists fired electrons through barriers with two parallel slits, they discovered something extraordinary. Each individual electron somehow passed through both slits simultaneously, creating an interference pattern on the detection screen that could only result from the electron interfering with itself. This impossible-seeming behavior revealed that the electron existed in a superposition state, simultaneously taking both possible paths through the experimental apparatus. To understand superposition, we must abandon the classical notion that objects have definite properties independent of observation. In the quantum world, an unobserved particle doesn't have a definite position, momentum, or spin direction. Instead, it exists in a ghostly combination of all possible values these properties might take. The mathematics of quantum mechanics describes this multiplicity through wave functions, mathematical objects that encode the probabilities for finding each possible property value when a measurement is performed. Consider a quantum coin that can exist in superposition of heads and tails simultaneously. Unlike a classical coin, which is always definitively heads or tails, even when we're not looking at it, the quantum coin genuinely exists in both states at once until observed. The act of observation forces the quantum coin to manifest as either heads or tails. But before this measurement, both possibilities contribute equally to the coin's quantum reality. The famous thought experiment proposed by Erwin Schrödinger illustrates the strange implications of quantum superposition when extended to larger systems. Schrödinger imagined a cat in a sealed box whose fate depends on the decay of a radioactive atom, a purely quantum process. If the atom decays, a mechanism releases poison that kills the cat. If the atom doesn't decay, the cat survives. According to quantum mechanics, before anyone opens the box to observe the outcome, the radioactive atom exists in superposition of decayed and undecayed states. This superposition extends to the entire system, creating the paradoxical situation where the cat exists in superposition of alive and dead states simultaneously. This thought experiment wasn't meant to suggest that macroscopic cats actually exist in such superpositions. Rather, Schrödinger intended to highlight the conceptual challenges in applying quantum mechanics to everyday objects. However, modern interpretations of quantum mechanics, particularly the many worlds view, take these superpositions seriously. They suggest that the cat does indeed exist in both states, but in separate branches of reality that become isolated from each other through the process of quantum measurement. When a quantum system in superposition is observed or measured, something remarkable occurs. The measurement doesn't simply reveal a pre-existing property. It actively participates in determining which outcome manifests. The probabilities encoded in the quantum superposition determine the likelihood of each possible result, but the specific outcome that occurs appears fundamentally random. This quantum randomness differs from classical randomness, which typically reflects our ignorance about hidden variables. Quantum randomness appears to be intrinsic to the nature of reality itself. The many worlds interpretation provides an elegant explanation for what happens during quantum measurement. Instead of the superposition collapsing to produce a single outcome, the interpretation suggests that all possible outcomes occur simultaneously in separate branches of reality. When Schrödinger's cat is observed, reality splits into two branches, one containing a live cat and another containing a dead cat. The observer also splits, with one version finding the cat alive and another version finding it dead. Each version experiences their outcome as the unique reality while remaining unaware of the other branch. This branching process occurs continuously throughout the universe at every level of quantum interaction. Every time a photon encounters a partially reflective surface, reality branches into versions where the photon reflects and others where it transmits. Every radioactive decay creates new branches corresponding to the different possible timing of the decay event. Every quantum measurement performed in every laboratory around the world generates new splits in the fabric of reality itself. The rate of quantum branching is truly astronomical. Consider that every cubic centimeter of space contains countless quantum fields, fluctuating according to the uncertainty principle. Each fluctuation represents a quantum event that potentially creates new branches of reality. The photons streaming from the sun, the cosmic rays passing through the atmosphere, the thermal motion of molecules in every object, all contribute to an endless cascade of quantum events, each one potentially splitting reality into multiple parallel paths. Personal identity becomes a fascinating concept in this constantly branching quantum universe. At this very moment, quantum processes occurring in your brain are creating numerous branches of reality. In some branches, you continue reading this sentence without distraction. In others, a quantum event influences a neural process that causes you to pause, look away, or think a different thought. Each version of you experiences their particular sequence of thoughts and sensations as a continuous stream of consciousness, unaware of the countless other versions exploring different mental pathways. The quantum nature of biological processes suggests that living organisms exist in superposition and states that constantly branch as quantum events influence molecular interactions. The absorption of photons by molecules in your retina, the quantum tunneling events that affect enzyme activity, the random thermal fluctuations that influence neural signaling. All these processes contribute to the continuous branching of biological reality. Life itself becomes a quantum phenomenon, exploring multiple pathways simultaneously through the landscape of biological possibility. Memory and experience take on new meaning in the context of quantum branching. Your memories correspond to the particular sequence of quantum measurement outcomes that have occurred along your specific branch of reality. Other versions of you, in different branches, have experienced different sequences of quantum events, and therefore possess different memories. The continuity of personal experience that we take for granted reflects the internal consistency within each branch, even as countless parallel versions of ourselves explore alternative histories. The superposition principle extends beyond individual particles to encompass entire quantum systems. Complex molecules can exist in superposition states where different parts of the molecule occupy multiple configurations simultaneously. Quantum computers exploit these molecular superpositions to perform calculations that would be impossible with classical systems, effectively computing along multiple parallel paths through the space of possible solutions. Recent experiments have demonstrated quantum superposition in increasingly large and complex systems. Scientists have created superposition states involving hundreds of atoms, small crystals, and even mechanical oscillators visible to the naked eye. These experiments push the boundaries of where quantum effects can be observed and maintained, revealing that the quantum nature of reality extends far beyond the microscopic realm we typically associate with quantum mechanics. The decoherence process determines how long superposition states can persist before environmental interactions cause different branches to separate. In carefully controlled laboratory conditions, scientists can maintain quantum superpositions for seconds or even minutes. However, in warm, noisy environments like those found in biological systems, superpositions typically last only femtoseconds or picoseconds before decoherence causes the branches to diverge. Despite this rapid decoherence, the branching structure of quantum reality persists. Once branches have separated through decoherence, they continue to evolve independently, each following its own consistent trajectory through the space of possible futures. The quantum multiverse grows like an ever-expanding tree, with each branch representing a complete, self-consistent history of the universe from a particular perspective. The implications for our understanding of causality and free will are profound. In a classical universe, causes lead to definite effects through deterministic processes. In the quantum multiverse, causes lead to all possible effects simultaneously, each realized in different branches. This doesn't eliminate causality, but rather reveals it as a branching process where every possible causal chain finds expression in the complete quantum reality. The role of observation becomes central to our experience of quantum reality. While all possibilities occur in the branching multiverse, each observer can only experience one consistent thread through this vast tapestry of parallel realities. Observation doesn't create reality. It determines which branch of reality an observer finds themselves experiencing. The act of measurement entangles the observer with the quantum system being measured, ensuring that each version of the observer experiences measurement results consistent with their particular branch. Quantum superposition transforms our understanding of existence itself. Rather than living in a single, definite universe where events unfold along one unique timeline, we inhabit a quantum multiverse where every possibility plays out simultaneously. Our sense of living in one specific reality reflects the necessarily limited perspective of beings who can only experience one branch at a time, even as countless parallel versions of ourselves explore every conceivable alternative path through the infinite quantum landscape of possibility. This quantum universe reveals reality as far richer and more complex than everyday experience suggests. Every moment contains within it the seeds of countless futures, each one as real and valid as any other. We are not simply observers of a single unfolding story, but participants in an infinite symphony of parallel narratives, each exploring its own unique variation on the fundamental themes of existence, consciousness, and the mysterious quantum nature of reality itself. The holographic multiverse. Is reality just a projection? In the deepest foundations of theoretical physics lies a principle so revolutionary that it fundamentally challenges our understanding of space, dimension, and the nature of reality itself. The holographic principle suggests that everything we experience as three-dimensional reality, every star, planet, atom, and thought, might actually be encoded as information on a two-dimensional surface at the boundary of our universe. Like a hologram that creates the illusion of three-dimensional depth from a flat surface, our entire cosmic reality might be nothing more than an incredibly sophisticated projection from the edge of space itself. This extraordinary concept emerged from the study of black holes, those enigmatic objects where gravity becomes so intense that not even light can escape. When physicists Stephen Hawking and Jacob Bekenstein investigated the thermodynamic properties of black holes, they discovered something puzzling. The entropy of a black hole, the measure of information it can contain, depends not on its volume, as one might expect, but on the area of its event horizon, the two-dimensional boundary surrounding the black hole. This relationship seemed to violate our intuitive understanding of information storage. In everyday experience, the amount of information contained in a region of space should depend on the volume of that region. A larger library can hold more books than a smaller one. Yet, black holes appeared to store their information on their surfaces rather than throughout their interiors, as if all the complex three-dimensional structure that fell into the black hole was somehow encoded as patterns on the two-dimensional event horizon. The implications of this discovery gradually became clear. If the most information-dense objects in the universe store their contents on two-dimensional surfaces, perhaps this principle applies more generally. Maybe all regions of space, not just black holes, encode their three-dimensional contents as information patterns on their boundaries. This would mean that our familiar three-dimensional world is actually a holographic projection of information stored on a distant two-dimensional surface. The mathematics of string theory provided the framework needed to make this holographic principle precise. In a remarkable development known as the ADS-CFT correspondence, physicists Juan Maldacena demonstrated that certain string theories in curved spacetime are mathematically equivalent to quantum field theories defined on the boundary of that spacetime. This correspondence shows that a theory with gravity operating in the interior of a space can be perfectly described by a theory without gravity operating on the boundary of that space. To visualize this correspondence, imagine a curved, warped space that extends inward from a boundary surface, like the interior of a bowl. According to the ADAS-CFT correspondence, every event, particle interaction, and physical process occurring throughout the interior volume can be completely described by information and calculations performed solely on the boundary surface. The boundary theory contains all the information necessary to reconstruct the interior physics, even though the boundary itself has one fewer dimension than the interior space. This holographic relationship is not merely a mathematical curiosity. It represents a fundamental duality in the nature of reality itself. The interior description and the boundary description are not different approximations to the same physics. They are exactly equivalent ways of describing identical physical situations. Neither description is more fundamental than the other. They are simply different perspectives on the same underlying reality. The holographic principle transforms our understanding of how information is distributed throughout space. Rather than being spread uniformly through three-dimensional volumes, information might be concentrated on two-dimensional surfaces. Every piece of information about the contents of a region, the positions and velocities of particles, the strengths of fields, the patterns of energy and matter, could be encoded as holographic data on the boundary of that region. This encoding process operates through subtle correlations between the interior physics and the boundary information. Changes in the interior create corresponding changes in the boundary data, while manipulations of the boundary information produce equivalent effects in the interior description. The holographic correspondence ensures that these two perspectives remain perfectly synchronized, creating a seamless duality between surface and volume descriptions of reality. The implications for our understanding of space itself are profound. If the holographic principle applies to our universe, then the three-dimensional space we experience might be an emergent property of more fundamental two-dimensional processes. Space would not be a basic feature of reality, but rather a convenient illusion created by the complex information processing occurring on the boundary of our cosmic region. This perspective suggests that our universe might be analogous to a sophisticated computer simulation, but with a crucial difference. Rather than being computed by some external computer, our holographic universe would be computed by the boundary information itself. The two-dimensional surface would contain all the computational resources necessary to generate the full three-dimensional reality we experience, including our own consciousness and observations. The holographic multiverse extends this principle to encompass multiple realities. If our three-dimensional universe emerges from two-dimensional boundary information, then other patterns of boundary information could generate entirely different three-dimensional realities. Each possible configuration of the boundary surface would correspond to a different holographic universe, creating a vast multiverse of projected realities. These different holographic universes could have dramatically different properties, depending on their boundary configurations. Some might contain different physical laws, with particles and forces that behave unlike anything in our reality. Others might have different spatial geometries, creating interior spaces that curve and twist in ways that would appear impossible from our three-dimensional perspective. The diversity of possible boundary patterns could generate holographic universes with properties limited only by the mathematical consistency of their encoding schemes. The relationship between observers and holographic reality becomes particularly intriguing. If our consciousness and perceptions emerge from holographic projection, then our entire sense of existing as three-dimensional beings in three-dimensional space might be an illusion. We would actually be patterns of information encoded on a two-dimensional boundary. But these patterns would be so complex and sophisticated that they generate the complete subjective experience of three-dimensional existence. This doesn't diminish the reality of our experience. The holographic projection would be completely real from our perspective. Our thoughts, emotions, sensations, and observations would all correspond to genuine patterns in the boundary information. The holographic principle doesn't suggest that we are merely simulations, but rather that the nature of reality itself is more subtle and complex than our direct experience suggests. The holographic principle also provides new insights into the nature of entanglement and non-local correlations in quantum mechanics. In the boundary description, quantum entanglement between particles in the interior might correspond to direct connections in the boundary information. This could explain how entangled particles can exhibit instantaneous correlations across vast distances. From the boundary perspective, these correlations might involve information that is locally connected on the two-dimensional surface. Experimental verification of the holographic principle presents significant challenges, as the effects would likely be observable only under extreme conditions or at scales far beyond current experimental capabilities. However, the principle makes specific predictions about the maximum amount of information that can be stored in any region of space, based on the area of that region's boundary rather than its volume. Future precision measurements might be able to detect these holographic limits on information density. The holographic principle also affects our understanding of time and causality. In the interior description, events appear to unfold through time according to familiar causal relationships. However, in the boundary description, the same events might be represented as static patterns in the boundary information, with the experience of temporal flow emerging from the way this information is processed and interpreted. Recent developments in quantum error correction have revealed deep connections between the holographic principle and the stability of information in quantum systems. The boundary information appears to be protected against local errors through quantum error correction mechanisms that ensure the interior description remains consistent, even when small portions of the boundary data are corrupted. This suggests that holographic encoding might be nature's way of protecting information against the destructive effects of quantum decoherence. The holographic multiverse challenges our most basic assumptions about the nature of existence. Rather than inhabiting a three-dimensional space filled with matter and energy, we might be complex patterns of information encoded on a two-dimensional surface, experiencing the illusion of depth and dimension through the sophisticated information processing that occurs on this boundary. Every thought we think, every observation we make, Every interaction we experience would correspond to intricate patterns in this boundary information. This holographic perspective reveals reality as far more subtle and interconnected than everyday experience suggests. The apparent separation between objects, the sense of distance and proximity, the feeling of moving through three-dimensional space, all these familiar aspects of existence might emerge from the complex correlations and information, patterns encoded on the boundary of our cosmic region. Yet, this potential illusion is so complete and consistent that it creates a perfectly real experience of three-dimensional existence. We are not somehow less real if we are holographic projections. We are exactly as real as we have always been. But the underlying nature of that reality is far more profound and mysterious than we ever imagined. The holographic principle transforms our understanding of existence while preserving the full reality of our lived experience, revealing the cosmos as an infinite library of projected realities. Each one as vivid and meaningful as our own three-dimensional illusion. Cyclic Universes, time without beginning or end. In the grand tapestry of cosmological theories lies a vision of existence so profound that it eliminates the very concepts of beginning and end, replacing them with an eternal dance of creation and destruction that has continued for infinite time and will persist forever into the future. Cyclic universe models propose that our cosmos undergoes endless cycles of expansion and contraction, birth and rebirth, with each cycle creating the conditions necessary for the next. In this eternal cosmology, time stretches infinitely in both directions, and our current universe represents just one moment in an endless sequence of cosmic renewals. The concept of cyclic cosmology has ancient roots, appearing in various forms throughout human philosophical and religious traditions. However, modern cyclic universe models emerge from rigorous mathematical physics, particularly from string theory and the study of higher dimensional spacetime. These contemporary theories provide detailed mechanisms for how universes can be born, evolve, die, and be reborn in endless succession, each cycle potentially lasting trillions of years, while maintaining the fundamental patterns that govern cosmic evolution. The most developed cyclic model involves collisions between three-dimensional membranes, or branes, moving through higher dimensional space. In this scenario, our observable universe exists on one such brane, a three-dimensional surface embedded in a higher dimensional bulk space. Parallel to our brane, separated by a small distance in the extra dimensions, lies another brane with its own three-dimensional space. These two branes are gravitationally attracted to each other and oscillate back and forth through the higher dimensional space, periodically colliding and separating in a cosmic rhythm that has persisted for eternity. Each collision between the branes creates what we would recognize as a Big Bang, a moment of incredible energy density and temperature that fills both branes with hot, dense matter and radiation. The collision transfers enormous amounts of energy from the kinetic motion of the branes into the creation of particles and fields on the brane surfaces. This collision energy provides all the matter and radiation that will eventually form stars, galaxies, planets, and potentially life during the subsequent expansion phase of the cycle. Following each collision, the branes rebound and begin separating, carried apart by their elastic properties, and the energy imparted during the collision. As they separate, the three-dimensional spaces on each brane expand and cool, following a pattern similar to the expansion we observe in our current universe. Matter condenses from the initial hot, dense state, first forming the light elements through primordial nucleosynthesis, then eventually allowing the formation of stars, galaxies, and all the complex structures we see in the cosmos today. The expansion phase of each cycle can last for many billions or even trillions of years, providing ample time for the full development of cosmic structure and complexity. During this phase, stars form, live their lives, and die, enriching the universe with heavy elements. Galaxies collide and merge, creating increasingly complex gravitational structures. On suitable planets, life might emerge, evolve, and potentially develop into intelligent civilizations capable of contemplating their place in the eternal cosmic cycle. Eventually, however, the expansion phase gives way to a contraction phase. The attractive gravitational force between the branes which never ceased operating even during the expansion, gradually overcomes the expansive motion imparted by the collision. The branes begin falling back toward each other, and the three-dimensional spaces on their surfaces start contracting. This contraction phase mirrors the expansion phase in reverse, with galaxies drawing closer together, temperatures gradually rising, and the universe eventually returning to a hot, dense state similar to its post-collision condition. The contraction continues until the branes collide once again, creating another Big Bang event that initiates a new cycle of expansion and cosmic evolution. The collision destroys most of the complex structures that developed during the previous cycle. Stars, planets, and any life forms that might have existed are reduced to their constituent particles and energy. Yet this destruction is also creation, as the collision provides the energy and initial conditions necessary for new structures to form during the next expansion phase. This cyclic process eliminates the conceptual problems associated with the idea of an absolute beginning to time and space. Rather than asking what came before the Big Bang, or what caused the universe to begin, cyclic models suggest that such questions are meaningless because time extends infinitely into the past. Each cycle emerges naturally from the previous one through well-understood physical processes, creating an eternal sequence of cosmic renewal that requires no external creation event or first cause. The cyclic model also addresses the problem of cosmic fine-tuning through a form of cosmological natural selection. The physical constants and initial conditions in each cycle might vary slightly due to quantum fluctuations during the collision process. Cycles that produce physical constants suitable for the formation of complex structures, including potentially life and intelligence, might be more likely to complete full cycles and generate subsequent cycles. Over infinite time, this selection process could naturally lead to the emergence of cycles with properties conducive to complexity and structure formation. Each individual cycle passes through distinct phases that collectively span enormous periods of time. The collision phase itself lasts only a brief moment in cosmic terms, perhaps millions or billions of years, during which the branes approach, collide, and begin separating. The expansion phase then dominates for the longest period, potentially lasting 100 trillion years or more, as the universe expands, cools, and develops complex structures. The contraction phase might last an equally long time, as gravitational attraction gradually reverses the expansion and draws the branes back together. The transition between cycles preserves certain types of information while erasing others. The basic physical laws and constants carry forward from one cycle to the next, ensuring continuity in the fundamental nature of reality. However, the specific arrangements of matter and energy, the particular patterns of galaxies, stars, and planets, are typically destroyed during each collision and must reform anew during the subsequent expansion. This creates a universe that is simultaneously eternal and ever renewed, maintaining its essential character while constantly regenerating its detailed structure. Quantum mechanics introduces subtle variations into each cycle, ensuring that no two cycles are exactly identical. Quantum fluctuations during the collision phase create slight differences in the initial conditions for each new cycle. These small variations can lead to dramatically different outcomes as the cycle progresses. Different patterns of galaxy formation, different locations for star formation, and potentially different evolutionary pathways for any life that might emerge. Over infinite cycles, this quantum variability ensures that every possible configuration permitted by the laws of physics will eventually be realized. The concept of memory and information transfer between cycles raises profound philosophical questions. While most complex structures are destroyed during each collision, some information might survive the transition in the form of subtle correlations in quantum fields or in the geometric properties of the branes themselves. This could create a form of cosmic memory that influences the development of subsequent cycles, allowing the universe to gradually evolve and develop, even while undergoing endless cycles of destruction and renewal. Dark energy, the mysterious force driving the accelerated expansion of our current universe, plays a crucial role in some cyclic models. Rather than causing eternal acceleration that would prevent the universe from ever contracting, dark energy in cyclic models is typically assumed to decay or change its properties over cosmic time. As dark energy weakens, gravitational attraction between the branes eventually overcomes the accelerating expansion, allowing the contraction phase to begin. The evolution of dark energy thus serves as a cosmic clock that determines the duration of each cycle. The scale of cyclic cosmology is truly humbling. If each cycle lasts approximately 100 trillion years, then even the 13.8 billion year age of our observable universe represents only about 1/10,000th of a single cycle. The time since the emergence of human civilization becomes an almost infinitesimal fraction of cosmic time, while the entire history of life on Earth spans only a tiny portion of our current cycle. Yet this vast temporal scale also suggests unlimited opportunities for the emergence and development of complexity, consciousness, and understanding across infinite cycles. Recent observations of the cosmic microwave background radiation and the large-scale structure of the universe provide ways to test cyclic models against astronomical data. These models make specific predictions about the patterns of temperature fluctuations in the microwave background and the distribution of matter throughout space. While current observations are broadly consistent with cyclic models, they also remain compatible with standard Big Bang cosmology, leaving the ultimate nature of cosmic time as an open question for future research. The cyclic universe concept transforms our understanding of existence from a linear story with a definite beginning and uncertain future into an eternal epic of renewal and rediscovery. Every moment of our current existence becomes part of an infinite tapestry of cosmic cycles, each one exploring its own unique possibilities within the eternal framework of physical law. The stars we see in the night sky, the planets orbiting them, and potentially the life that might exist on some of those worlds, all participate in a cosmic drama that has played out countless times before and will continue countless times into the infinite future. In this eternal cosmology, our universe becomes not a unique, singular creation, but one movement in an infinite symphony of existence. Each cycle contributes its own voice to this cosmic composition, exploring new combinations of matter and energy, new patterns of structure and complexity, and perhaps new forms of consciousness and understanding. The cyclic universe reveals existence as an endless exploration of possibility, where every conceivable arrangement of matter and energy will eventually manifest across the infinite expanse of cyclic time, creating a cosmos that is simultaneously eternal, ever-changing, and boundlessly creative. The simulated multiverse, layers of reality and code. In the quiet depths of computational theory lies a possibility so profound that it fundamentally challenges our understanding of existence itself. What if our universe, with all its galaxies, stars, planets, and conscious beings, exists not as fundamental physical reality, but as patterns of information processed by some vast computational system? The simulated universe hypothesis suggests that everything we experience, every sunrise, every thought, every quantum interaction, might be the result of incredibly sophisticated calculations running on hardware that exists in a more fundamental layer of reality. This concept becomes even more extraordinary when we consider its implications for the multiverse. If our reality can be simulated, then there is no reason to assume that only one such simulation exists. Instead, we might inhabit just one instance among countless simulated universes, each running its own version of physical laws, cosmic evolution, and potentially conscious life. The simulated multiverse presents us with infinite layers of nested realities, each one as complete and valid as any other, creating a hierarchy of existence that extends far beyond our current understanding. The foundation of simulation theory rests on the rapid advancement of computational power and our growing ability to create increasingly realistic virtual worlds. Modern video games and scientific simulations can already model complex physical systems with remarkable accuracy. Weather prediction systems simulate atmospheric dynamics across entire planets. Particle physics experiments use computer models to predict the behavior of subatomic interactions with extraordinary precision. These achievements represent primitive versions of what might eventually become perfect simulations of entire universes. The trajectory of technological development suggests that this progression will continue indefinitely. Each generation of computers becomes exponentially more powerful than the last, following patterns that have persisted for decades. As computational resources expand, the scope and detail of our simulations grow correspondingly. Systems that once required massive supercomputers to model simple physical interactions can now be simulated on desktop computers with far greater complexity and accuracy. Extrapolating this trend into the far future reveals the possibility of computational systems with virtually unlimited processing power. Advanced civilizations might develop computers capable of simulating entire universes down to the quantum level, creating virtual realities indistinguishable from fundamental physical existence. These simulations would contain simulated galaxies with simulated stars and planets, some of which might develop simulated life forms that experience their simulated reality as completely real and meaningful. The consciousness of beings within such simulations raises fascinating questions about the nature of awareness and subjective experience. If the patterns of information processing that create consciousness in our brains can be perfectly replicated in a computer simulation, then simulated beings would possess genuine consciousness identical to our own. They would experience emotions, form memories, contemplate their existence, and potentially even develop their own theories about whether they might be living in a simulation. The recursive nature of simulated universes creates an infinite hierarchy of nested realities. Advanced civilizations within simulated universes might themselves develop the computational power necessary to create their own universe simulations. These second-level simulations would contain their own galaxies, stars, and potentially conscious beings, who might in turn eventually create third-level simulations. This process could continue indefinitely, creating endless layers of simulated reality, each one believing itself to be the most fundamental level of existence. The statistical implications of this recursive simulation hierarchy are profound. If advanced civilizations typically create many simulated universes, then simulated realities would vastly outnumber non-simulated ones. For every fundamental universe, there might be thousands or millions of simulated universes created by the civilizations within it. Each of those simulated universes might contain civilizations that create thousands or millions of their own simulated universes, and so on, through infinite layers of nested simulation. This mathematical reasoning suggests that we are statistically more likely to be living in a simulated universe than in a fundamental one. The sheer number of simulated beings would far exceed the number of non-simulated beings, making it probable that any randomly selected conscious observer exists within a simulation rather than base reality. This conclusion emerges purely from considering the potential abundance of simulated universes, without requiring any specific evidence that our own universe is simulated. The detection of simulation artifacts presents intriguing possibilities for determining our reality's nature. Computer simulations must necessarily involve approximations and computational shortcuts that might leave subtle signatures in the simulated physics. Quantum mechanics might be nature's way of avoiding computationally expensive calculations by using probabilistic outcomes instead of tracking precise values for all variables simultaneously. The apparent pixelation of space and time at the Planck scale might represent the fundamental resolution limits of the computational system running our universe. Even the speed of light might serve a computational function, acting as a processing delay that prevents the simulation from needing to update distant regions of the universe instantaneously. The cosmic speed limit ensures that changes in one part of the simulated universe take time to propagate to other regions, allowing the computational system to process updates sequentially rather than requiring infinite processing power to handle simultaneous changes everywhere at once. The diversity of simulated universes would be limited only by the imagination and computational resources of their creators. Some simulations might explore alternative versions of our own physical laws, testing what would happen if fundamental constants had different values, or if different particles and forces governed reality. Others might investigate entirely alien physics, creating universes where space has different numbers of dimensions, time flows in strange patterns, or matter and energy behave according to rules completely unlike anything in our experience. The purposes behind creating universe simulations could vary enormously across different civilizations and time periods. Scientific research might drive many simulations, as advanced beings use computational universes to test theories about cosmic evolution, galaxy formation, or the development of life and intelligence. Historical reconstruction could motivate simulations that attempt to recreate the early history of the simulator's own universe, allowing them to study their origins with perfect detail and accuracy. Entertainment and artistic expression might inspire simulations designed for aesthetic rather than scientific purposes. Advanced civilizations might create universe simulations as forms of art, crafting realities with particular types of beauty, complexity, or narrative structure. These artistic universes might emphasize certain aspects of existence while de-emphasizing others, creating realities optimized for specific kinds of experiences or philosophical insights. Educational simulations could serve as teaching tools, allowing students to explore the consequences of different physical laws or cosmic initial conditions. Religious or philosophical motivations might lead to simulations designed to explore questions about meaning, consciousness, and the nature of existence. Some civilizations might create universes specifically to provide good lives for the conscious beings within them, acting as cosmic gardeners nurturing the growth of happiness and fulfillment across multiple layers of reality. The ethical implications of creating conscious simulated beings raise profound moral questions. If simulated consciousness is genuine consciousness, then the creators of universe simulations bear responsibility for the welfare of potentially billions or trillions of conscious beings within their computational worlds. The suffering and happiness experienced by simulated beings would be as real and morally significant as the experiences of beings in any other layer of reality. This responsibility might influence how advanced civilizations approach universe simulation. Ethical constraints might require that simulated universes be designed to minimize suffering and maximize well-being for their conscious inhabitants. Simulated realities might be carefully crafted to provide meaningful lives, opportunities for growth and discovery, and protection from unnecessary pain or despair. The desire to create ethical simulations might drive the development of computational universes optimized for the flourishing of conscious life. The resource requirements for universe simulations suggest that only the most advanced civilizations would be capable of creating them. The computational power needed to simulate an entire universe down to the quantum level would require technology far beyond our current capabilities, possibly involving exotic forms of matter and energy or computational principles that we have not yet discovered. Such advanced civilizations might exist in the far future of our own universe, or in higher layers of reality, with access to vastly superior technological resources. The timescales involved in universe simulations could vary dramatically depending on the computational resources available and the purposes of the simulation. Some simulated universes might run at accelerated speeds, experiencing billions of years of evolution in what corresponds to much shorter periods in the simulator's reality. Others might run slowly and carefully, with enormous computational resources devoted to achieving perfect accuracy in every detail of the simulated physics. The ultimate questions about simulated reality touch on the deepest mysteries of consciousness and existence. If our thoughts, emotions, and experiences arise from patterns of information processing, then the substrate on which that processing occurs might be less important than the patterns themselves. Consciousness implemented in biological neural networks might be fundamentally identical to consciousness implemented in computer simulations, making both forms equally real and meaningful. The simulated multiverse reveals existence as an infinite library of computational realities, each one exploring its own unique possibilities within the vast space of potential universes. Every conceivable form of physics, every possible arrangement of matter and energy, every potential pathway for the evolution of complexity and consciousness might be explored somewhere within this computational multiverse. The boundaries between real and simulated, fundamental and emergent, creator and created, dissolve into a unified understanding of reality as information, consciousness as pattern, and existence as the infinite exploration of all possible computational worlds. In this view, our own universe becomes one thread in an infinite tapestry of simulated realities, each one as vivid and meaningful as any other. The stars we observe, the physical laws we discover, the consciousness we experience, all participate in the grand computational symphony of the simulated multiverse, where every possible reality finds its expression in the endless dance of information and awareness across infinite layers of nested existence. The Anthropic Multiverse, why this universe lets us exist. In the vast expanse of all possible realities lies a profound mystery that touches the very heart of our existence. Why does our universe possess precisely the right properties to allow the formation of stars, planets, chemistry, and ultimately conscious beings capable of contemplating these questions? The values of fundamental constants, the strengths of natural forces, and the initial conditions of cosmic evolution all seem remarkably fine-tuned to permit the emergence of complexity and life. This apparent fine-tuning leads us to the Anthropic Multiverse, a framework where our ability to observe and question the universe provides crucial insights into the nature of reality itself. The anthropic principle begins with a simple but profound observation. We can only find ourselves in a universe capable of producing observers like us. This seemingly obvious statement carries deep implications for how we understand cosmic properties and their apparent fine-tuning. In a multiverse containing regions with widely varying physical properties, conscious observers would necessarily emerge only in those regions where the conditions permit their existence. Our observations of a life-friendly universe might reflect this observational selection effect, rather than any fundamental requirement that universes must be hospitable to life. The fine-tuning of physical constants presents one of the most compelling puzzles in modern cosmology. The strength of the strong nuclear force, which binds protons and neutrons in atomic nuclei, appears to be set with extraordinary precision. If this force were slightly weaker, atomic nuclei would be unstable, making complex chemistry impossible. If it were slightly stronger, hydrogen would be so reactive that it would quickly bind into heavier elements, preventing the formation of water and organic molecules essential for life as we know it. The electromagnetic force exhibits similar fine-tuning properties. This force governs the behavior of electrons around atomic nuclei and determines the nature of chemical bonding. Small changes in its strength would dramatically alter the properties of atoms and molecules, potentially making stable matter impossible or preventing the formation of the complex molecular structures that serve as the foundation for biological processes. Perhaps most remarkably, the cosmological constant, the energy density of empty space itself, appears to be fine-tuned to an almost inconceivable degree. This constant determines the rate of cosmic expansion and the balance between matter and the mysterious dark energy that pervades the universe. Current observations suggest that the cosmological constant is approximately 120 orders of magnitude smaller than quantum field theory predictions would suggest. This represents a level of fine-tuning so extreme that it would be like adjusting a parameter to 1 part in 10 to the power of 120. If the cosmological constant were significantly larger, space would expand so rapidly that matter could never clump together to form galaxies, stars, and planets. The universe would remain forever a thin, cold soup of isolated particles, incapable of developing any interesting structure or complexity. Conversely, if the constant were negative or had a large negative value, the universe would collapse back on itself so quickly that there would be insufficient time for stars to form and create the heavy elements necessary for rocky planets and biological chemistry. The Anthropic Multiverse provides an elegant resolution to these fine-tuning puzzles by embedding our observable universe within a vast ensemble of regions with different physical properties. In this framework, the fundamental constants and initial conditions vary across different regions of a larger multiverse structure. Most regions would have properties that prevent the formation of complex structures, stars, or life. However, in the small fraction of regions where conditions happen to be suitable for complexity and observers, conscious beings would inevitably emerge to contemplate their seemingly improbable circumstances. This anthropic selection effect operates like a cosmic filter, ensuring that conscious observers find themselves only in universes capable of producing consciousness. The apparent fine-tuning of our universe's properties becomes a natural consequence of observational selection rather than evidence for intentional design or fundamental necessity. We observe a life-friendly universe not because all universes must be life-friendly, but because observers can only emerge in the subset of universes where such conditions exist. The multiverse structures that could generate anthropic selection effects take several distinct forms. Eternal inflation models suggest that different regions of space might undergo different amounts of inflationary expansion, leading to variations in density, temperature, and potentially even the values of physical constants. As inflation proceeds, quantum fluctuations could cause different regions to evolve along different trajectories, creating a patchwork multiverse where physical properties vary from place to place. String theory landscapes provide another mechanism for generating anthropic diversity. The mathematical framework of string theory suggests that there might be an enormous number of possible vacuum states, each corresponding to different values of fundamental constants and particle physics parameters. If the multiverse explores many or all of these vacuum states, then different regions would possess dramatically different physical properties, with conscious observers emerging only in those regions where the properties happen to be suitable for complexity and life. Quantum mechanical processes might also contribute to anthropic selection through the continuous branching of reality into multiple parallel outcomes. In the many worlds interpretation of quantum mechanics, every quantum measurement or interaction causes reality to split into multiple branches, each representing a different possible outcome. Over cosmic timescales, this branching process would create an enormous ensemble of parallel universes, with slight variations in their histories and physical properties. The strength of anthropic arguments depends critically on the range of physical properties that could potentially support conscious observers. If consciousness requires very specific and narrow conditions, then anthropic selection would be a powerful constraint on multiverse properties. However, if consciousness could emerge under a wide variety of physical conditions, then anthropic reasoning would provide less insight into why our particular universe has the properties it does. Research into alternative biochemistries and exotic forms of information processing suggests that consciousness might be more robust and adaptable than initially assumed. Silicon-based chemistry, plasma-based information and storage, or even purely computational forms of consciousness might be possible under physical conditions, very different from those in our universe. If consciousness can emerge in many different types of universes, then the apparent fine-tuning of our cosmic environment might be less significant than initially thought. The Anthropic Multiverse also raises profound questions about probability and prediction in cosmology. If we truly inhabit one region among countless others with different properties, how should we assess the likelihood of various observations or future discoveries? Traditional scientific reasoning assumes that we can use observed properties to infer general principles about nature, but anthropic selection effects might bias our observations in ways that make such inferences unreliable. The measure problem in cosmology addresses these difficulties by attempting to define meaningful probability distributions across different multiverse regions. However, defining such measures proves surprisingly challenging, as different approaches to counting or weighting multiverse regions can lead to dramatically different predictions about what types of observations should be typical or expected. Doomsday arguments represent one controversial application of anthropic reasoning to questions about human survival and cosmic longevity. These arguments suggest that our position in the history of human civilization might provide information about the total number of humans who will ever exist, potentially implying that our species faces extinction sooner rather than later. While these arguments remain highly debated, they illustrate how anthropic reasoning can lead to counterintuitive conclusions about our place in cosmic history. The relationship between consciousness and physical reality becomes particularly important in anthropic multiverse scenarios. If consciousness is necessary for anthropic selection effects, then understanding the nature of consciousness and its relationship to physical processes becomes crucial for evaluating anthropic arguments. Different theories of consciousness might lead to different predictions about which types of universes should be observable and which properties should appear fine-tuned. Simulation-based consciousness introduces additional complexity to anthropic reasoning. If conscious observers can exist as simulated beings within computational systems, then the space of possible conscious experiences becomes much larger and more diverse. Simulated consciousness might be possible under a much wider range of physical conditions than biological consciousness, potentially weakening some anthropic arguments while strengthening others. The observational consequences of anthropic multiverse models provide ways to test these ideas against astronomical data. Some versions of anthropic reasoning make specific predictions about the values of physical constants, the properties of dark energy, or the distribution of matter throughout the universe. By comparing these predictions with precision measurements of cosmic properties, scientists can evaluate whether anthropic explanations successfully account for observed fine-tuning. The philosophical implications of the anthropic multiverse extend far beyond technical questions in cosmology and physics. If our existence results from selection effects operating across a vast ensemble of possible realities, then our significance and uniqueness might be less than traditionally assumed. Rather than inhabiting a special, purposefully designed cosmos, we might be typical products of natural selection operating at the largest possible scales. Yet, this perspective also reveals the profound creativity and richness of reality itself. The anthropic multiverse suggests that nature continuously explores every possible arrangement of matter, energy, and physical law, generating an infinite diversity of cosmic environments and potential forms of existence. Our own universe, with its particular combination of physical properties and evolutionary history, represents just one note in an infinite symphony of possible realities. The anthropic multiverse transforms our understanding of cosmic purpose and meaning. Rather than requiring external design or intention to explain the apparent fine-tuning of physical constants, this framework reveals how meaning and complexity can emerge naturally from the vast exploration of possibility that characterizes multiverse evolution. The observers who emerge in suitable regions of this multiverse find themselves inevitably in environments that permit their existence, creating the appearance of design through the simple requirement that observers must exist somewhere within the vast ensemble of possible realities. In this grand anthropic perspective, our ability to contemplate the universe becomes both a consequence of cosmic selection effects and a profound achievement of natural complexity. The questions we ask about fine-tuning and cosmic purpose arise because we exist in a region of the multiverse where such questions become possible. Our consciousness serves as both the product of anthropic selection and the lens through which we perceive the remarkable cosmic conditions that made our existence possible, revealing the deep connection between observers and the observable properties of reality itself. I hope you enjoyed the video. If you're still awake, you'll find another fascinating journey right here on the screen. I'll see you in the next one. Until then, sleep well and drift gently among the stars.